Okay, we start a new chapter, chapter 9. And this is Bach, due to a physicist whose name is Per Bach. Shortest name of a physicist, probably. Okay, so what is it about? It's about a concept called self-organized criticality. Okay, so let me make a connection with the previous chapter. So fractals are everywhere, right? In space. Why do we call this a fractal? It's an image of, probably Google Earth image of some terrain, right? But if you get closer, it still has similar kind of complexity. So it's in space or in time, right? Do I also have, yeah. What do I mean by in time? If I erase these years, if I erase these values and just concentrate, zoom in here, if you have enough quality data, you wouldn't be able to tell whether I have zoomed in US dollar, euro parity, or haven't zoomed in. You wouldn't be able to tell. It would be self-similar, right? So then there is this paper, 1986, very famous statistical physicist Kadanoff writes in Physics Today, "Why all the fuss about fractals? Physical Review Letters complains that every third submission seems to concern fractals in some way or another. Corporate research labs such as Exxon and IBM expend perceptible fractions of their entire basic research budgets on the study of fractal systems. Perhaps a half dozen conferences during the past year were devoted to the subject. Apparently in 1986, half a dozen conferences were too much. And now it's like Wednesday, right? Why? And then there is a whole like 2 pages about it, and finally he closes with this. Without that underpinning, much of the work on fractals seems somewhat superficial and even slightly pointless. It is too easy to perform computer simulations upon all kinds of models and to compare the results with each other and with real-world outcomes, but without organizing principles, the field tends to decay into a zoology of interesting specimens." How do I read this one? And facile classifications, yes? What does it mean? I don't know. Like hurried, I guess, right? Despite the beauty and elegance of the phenomenological observations upon which the field is based, the physics of fractals, in many ways, a subject waiting to be born, 1986. Now we go to 1987, and this guy, Per Bach, writes this paper, Self-Organized Criticality, an Explanation of 1 over F noise. And inside, he cites this article and says, fractal structures to be widespread in nature, the physics of fractals could be that they are the minimally stable states originating from dynamical processes which stop precisely at the critical point. Now, we will try to understand this sentence throughout this chapter, and we will write simple programs, and they will help you, hopefully. But he took it to, it wasn't just one paper and he let it go. No, he wrote a book with a title that promises a lot, How Nature Works, and the Self-Organized Criticality. I've mentioned this book, if you remember, right at the beginning of the lecture. So he connects everything to self-organized criticality, and the book starts with this. How do we know that the creations of worlds are not determined by falling grains of sand? It starts with this. And it's apparently in Victor Hugo's the Miserables novel. Okay, what it has to do with sands, let me explain. We are going to talk about Sandpile model first. Sandpile model. Let me talk about sand a little bit, but then we will simplify it a lot. Imagine you are in a beach. You are just pouring sand and it's very dry. It doesn't stick necessarily, okay? So the sand starts lumping up. You keep pouring, right? It will reach to certain critical angle, after which every time you put a sand grain, most probably you will have some event, right? Sometimes that event will be just you put a grain and it doesn't stay at the top, it just falls. So an event of size 1, okay? Every now and then you will put another sand and the sand will fall, but it will be too much for this part, so it will fall too, a size 2 event. And sometimes, every now and then, it will just, the whole thing will suddenly move, like there will be this kind of a toppling. Like one will topple the other, one will topple the other, one will topple the... Although the perturbation was the same. Okay? So we are going to build a model, a very simple model of this, and we are going to investigate how these avalanches of activity are behaving. Okay, let me make a grid of 4 by 4. I can just put maybe 5 by 5, I don't know, maybe 5 by 5. So the model starts with this. You can put numbers between 0 and 3. Okay. No. Yeah. So let's, this is the initial condition. Let's now put a grain. I will explain you the rules of this game. Let's say I put a new grain over here and it becomes 4. Well, when it becomes 4, it's no longer stable, it will topple. That's the rule of our Sandpile model, okay? When it's 4 or above, that value goes -4, like it goes down to 0, and those 4 grains of sand go to the neighborhood, okay? Making this one 3, 2, 3, 4.
Oops, another 4.
Oops, another 4, exactly. Oops, another 4. And another 4 should go to 0. So we already had an event here, right, where we put the sand, but that event spread out to here as well, right? And after that one topples, this becomes 0, and these ones 3, 1, 1, 1. And does it stop? Yes. Yes, it does stop. But it could not stop, maybe, right? That was also a possibility. So if I put another grain here, it becomes just 1, and no toppling happens. So sometimes you put a grain of sand, but nothing happens, right? So what we are going to do is we are going to look at a code.
I have a question.
Yes.
What happens something at boundary becomes...
Oh, yeah, that's very, very important. That's very, very important. Let's say I put a grain of sand here, and it becomes 4. I shouldn't, okay. Let me just copy this one. Let's say I put it here, and this becomes 4, but then it goes down to 0, right? It topples and makes this one 3 and this one 1. What happens to these ones? They just fall off the table. Okay? Why? Because if we don't do this, everything just becomes super critical and keeps toppling, never stops. We don't want that. Okay? Okay, very good. So every step you take. We are going to see every step we take. And let's analyze this code. So let's say we have a particular state, and this n and m is going to be the indices where we put the new grain. Okay. So what is it called? Breadth first search? Do you know that? Depth first, breadth first search? Any computer scientists here? No computer scientists? Okay. Okay, it's like, okay, here is what I'm trying to say. So the logic here is that when this one becomes 4, I shouldn't really mess up these figures. Let me just copy them. Actually, I want to copy this one, and I'm going to work on that one. Copy, paste. So in our tuple function, let's say this is in this 0, 1, 2, 0, 1, 2. So I start with these 2 by 2, and once it becomes 4, it becomes a parent site. Okay, it becomes a parent, and it makes children here. Okay, then those children become parent, and you apply the same logic to those children. Okay, that's what's going on here. Let me show you. So my parent site is wherever I put my grain, and I increase that site by 1. Then while I have parent sites, if there are no parent sites left, if you remember at the end of the process there were no parent sites. If I do have, then I start with empty children sites, and then I do this. If the state in that parent site is greater than 3, then I count it as one event. I started with an avalanche of zeros, so I put 1 in that place where that toppling happened. I decrease that state by 4, I subtract 4. Then this is neighborhood, right? To the left, no. To the right, to the left, up and down. For all them, if they don't fall out of the table, if they remain within the table, then they are the children sites. And at the end, parent sites become children sites. No, children sites become parent sites. So I start here. I see whether there is a toppling. If there is a toppling, it makes children. Then those children become parents, right? I look whether this one toppled. If it did, it creates children of its own. But if it didn't, just it's the end of the story. Okay. So this whole thing tells me how many topplings happened, and where those topplings happen. So it returns the new state, the avalanche, which parts have been changed, and the total number of changes. Okay? So let's do it. And I'm going to plot only the avalanche. Okay? Not the state itself. This is very important. This is very important and intriguing. If you look at the state itself, you will see nothing. I will show you. But if you look at the avalanches, okay, it's these tiny avalanches here and there. Do you see them? Do you have any questions? Are you sure that you do understand this? No questions? What was it? Every step you take, right? I wish I had another code where it was every move you make, etc. But so this one, okay, did I enter? Yes. The next one is the same code. We are just going to plot it every time it breaks a record avalanche. So there are tiny bits of avalanches, and we are plotting each one of them, right? We are losing a lot of time. So let's just plot every time the avalanche breaks a record of largest avalanches. Does it make sense? So how do I achieve that? I have a maximum avalanche set to 0. If the count is greater than maximum avalanche, I plot it and set the new maximum avalanche to that count. Are you still with me? This will go, okay, that's a surprise. You see, this quickly turns into geography. Do you see it? And this is such a huge avalanche that the next record, we have to wait for the next record. Yeah. So let me ask you, what are these colors?
The height is at that point.
But why do you have a height?
Whether this is 0, 1, 2, or 3.
Oh no, that's absolutely not the case, because if I plot the state, okay. Every state you plot, okay. Let me just copy from here. As I promised, you will see nothing in the states. Very anticlimactic. Do you see? It's just, I'm even surprised to see these things. Probably it was in the middle of running, so there are a few 4s here, which shouldn't be the case. So let me just run this one more time, and let me just run it, and let me plot it here. Yeah, this is how normally the state looks like. There are 0s, 1s, and 3s, but you don't see anything. But when you plot the avalanches, you do see some structure that is hidden behind these 0s, 1s, and 2s, and 3s. Oh yeah, oh yeah. The answer to the previous question is that one. Yes, let's do it again. So remember, in these examples, we saw that we put one grain, it creates an avalanche, but at some point the avalanches become so large that they return. So it just starts toppling, comes back, topples, comes back, topples. So every time it comes back, it adds to that avalanche. That's why you create this terrain. Okay? How are we doing with this model? The big question is, so what, right? That's the big question here. Okay. To understand so what, we need to look at it very, very carefully. It's very hard to grasp this subject, so be aware of that. So, by the way, in case I forget, self-organized criticality is very connected to earthquakes. Okay, indeed, you know how they would say you can't predict one? You can't, indeed. So there was a seminar organized by Bill Kent University after the earthquake, the last one, the big one. And I was there, and it was someone who obviously knew what he was talking about. And at some point he said, you can't know them, but we know that it's connected to self-organized criticality. I was very happy that it was out there, like everybody knew that it's connected with that, in a sense that, okay, you can't predict it. How on earth can you draw fault lines if you can't predict? You can't predict when it will happen, but you can predict which sides are are in danger, which geographical places are in danger. That's possible. So let's do it with this very simple model, okay? Fault lines. So what we are going to do is this. As you can see, when you look at the states themselves, nothing can be seen, no pattern. And once the avalanche happens, it's too late, right? The avalanche happened. Of course, you can say that, okay, the earthquake was here, okay? That's no prediction. But can we do better? I think we can with this code. We can do the following. So I take my state. Right now, I have a state of 0, 1, 2, and 3s, right? Then I put a grain here and see where the avalanche is. I put a grain here and see where the avalanche is. Put a grain here. So I simulate every possible disturbance in that state. So I put a grain, the state changes, I reverse the state, put another grain again. So I try everything, right? And once I try everything, I get a map, okay? And in my map, you will see that at the beginning, if you remember at the beginning when we were plotting every step, there were these tiny islands, okay? So those tiny islands correspond to this. If I put a grain here, there will be an avalanche there. If I put a grain here, there will be an avalanche there. But those tiny avalanches has not connected to each other yet. So we will see how they start connecting, getting connected, and how it leads to a map with this code. So let's try to understand this code. This is the same toppling function. Okay, are you with me, by the way? Yes. Same toppling function. The only change is this change. Do you see? Change. It's different. So what this change does, this change just records the total change. Can I think for a moment? Yeah. It basically records how that state changed in total. Because whenever state is +1, change is +1. Whenever it's -4, it's -4. Whenever state changes +1, change is +1. It's just reporting the change. But what we do here, we start running the system, and then once the maximum count is above some threshold, we don't. Okay, let me explain the code. Sorry, I went back and forth. This is the same code, right? Same code. If you remember, in the previous one, we drew the state every time it broke a record, right? Now we will record the record. We will record the record, okay? But we will only start plotting once the record is above 1,000. So far, so good? Good. We will also record every step which had an avalanche of larger than 10. What do we do once we are here, once we have the maximum record and the count is above 10? We go over every step. Do you see? For n in range 1 to n-1, m in range 1 to n-1, we have a state, we have a copy of the state, and for every disturbance, we are counting the local change, and we are adding it to the total count. Did you follow this? Very good. So ignore this one. What this one is doing is just running the state forward. Okay, it's putting it at random sites and calculating the avalanche. Whenever the count of the avalanche is greater than the maximum count, then the new maximum count becomes count. So it makes sure that it keeps the record of the maximum counts, right? So if this was not there, there was nothing to plot. But once that maximum count starts going above 1,000, we start plotting. Okay? Was this clear? We can set it to 0 for now, so we will start counting right away. Okay? We will just start counting, we will just start plotting once the size is big enough. Just if it's above 10, you see, this part is really a meticulous calculation, because in that part you are doing 200 times 200 topplings, like at least 200 by 200 trials. You put the grain here, see what happens. Put the grain here, see what happens. Put the grain here, see what happens. You do it for every site. And then you keep the total change. Okay? Then we are going to plot the total change. Does it make sense? So that way, we are able to, is that the word, pierce? To look behind? Yes. Peek. Pierce is like delerek bakmak. So that word is better, I think. Like behind the curtain, behind those zeros, ones, and twos, and threes, they are actually self-organized in such a way that you can see at the background which sites are in danger right now. Okay, let me run the code. And okay. So what we are seeing here, let me explain each one by one. You see the background. There is something that goes from violet to bright colors. That background is total change, okay? So we added a grain here, we added a grain here. Apparently the grains added here had an effect, so it's a bit bright colored. Okay, what are these red dots? Those red dots, we are also keeping the count of total count. these red dots are the points where the total count is above 10 times the mean. So the whole terrain, each site has a total count. Like I put there a grain and I know how big an earthquake, let's speak in terms of earthquake. I know if I put the grain here, how big the earthquake will be, right? So out of all those earthquakes, if I take an average, multiply it by 10, the places where it is 10 times more likely than the mean are these red dots. Good? And you can see that those red dots are having a halo around them. And that halo is basically what Perbach was trying to say. I guess it's very hard to understand it. So basically the point is this: it organizes in such a way that if I put it here, it goes and the domino stops somewhere, right? At a boundary. If I start from here, it stops at that boundary. Start here, stops at that boundary. So since disturbing different points results in stopping at the same part, that part becomes brighter. So we start seeing, you see, we are expecting an earthquake here right now. And okay, one happened here. I mean, we are expecting an earthquake everywhere, but we are expecting a big one here. Does it make sense? And that happened, right? We are expecting a big one here. Let's see. At some point it will happen. Yeah, there you go. Does it make sense?
Yeah.
Are you sure? Let me.
What were these halos again?
What were these halos? Very good question. First of all, let me run it again so that we see also at the beginning you can see that all these pieces are just islands. They are there for no reason, just accidental stuff, okay? But once, I will answer your question soon. Once they are released, they stop at some point, right? So they create a potential new place for the earthquake. So they start coalescing. Those small things, it blows up here, it blows up here. It makes a structure that basically connects the two. So that makes a bigger potential place for disturbance. And then sometimes those potential disturbances just release and create smaller structures. But sometimes they coalesce and make bigger structures. What are these halos? Basically, those halos are created by plotting the count of total change. Okay? Total change. I put it here. Actually, let me show you something. You are still with me? Yeah. As you can see, I am plotting absolute value of the total change. Let me not plot absolute value. Let me instead plot the total change itself and put this to minus 300. And I don't want to wait, so I will put this to 1,000. So I will skip the self-organizing part where you see we are already in the self-organized part. So now the halos, do you see they are at the outside, usually it's yellow, at the inside it's black. Now why is that? Here is why. there's a domino and it falls down, falls down, falls down until it comes to a place where it stops. It can't fall down anymore. So what happens is that the last domino goes beyond there, adding to that line. I start from here, domino adds to that line. Start from here, domino, 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 adds one here. But to add one there, it removes 4 from here. So that's why its total count is negative here at the boundary, positive right outside. Does it make sense?
Yeah.
Yes? Okay, we expect an earthquake here. Okay, also there, but yes. You see, there was a large event there which reshaped this terrain, right?
Also, this looks like England.
Also, this looks like England. This looks like France. Yeah, about that. Why these things look like geographical things that has all kinds of, roughness that creates that coastline paradox. You remember? Now, why is that? Because, for example, this terrain over here may be created with a small event. Oh, there you go. We were expecting one, we got one, right? And what it left behind, there was a huge terrain here. It separated into 3 parts, right? But it goes both ways. Sometimes big structure creates smaller structure, and smaller structures create bigger structures, and everything is connected to each other, right? After self-organized criticality is reached. So that's why, for example, these sites may be created by smaller events, okay? This site may be created by a bigger event. The whole thing is created by a larger event, etc. So you have what Perbach is proposing is that this is the physics of fractals. This is how you get fractal structures, because if you reach this critical point, you can compare it with the criticality in Ising model. If you remember, in Ising model we had the ordered part, which had huge domains and smaller, tinier domains within those. Do you remember? At low temperature. At high temperature, you have just small domains, right? Right at the criticality, you have domains of all sizes. Do you remember that? Yes? Now, you reach that criticality by tuning a parameter. But this is self-organized criticality. So this is appearing without needing for tuning. This is appearing by itself. Why it is appearing? Because smaller events morph terrain in a small way, bigger events in a big way, but both are connected. So indeed, if you, let's go to,
I have another question. Before starting, if we had made simulation in a far bigger grid and then zoomed in, will we be able to discern?
no. I mean, if you reach the critical point, if you wait for long enough, the system self-organizes into a critical state which has that self-similarity. Look, at the critical point, there is a distribution of clusters of all sizes. Local perturbation will therefore propagate over all length scales, leading to fluctuation lifetimes over all time scales. A perturbation can lead to anything from a shift of a single pendulum to an avalanche, depending on where the perturbation is applied. The lack of a characteristic length leads directly to a lack of a characteristic time for the resulting fluctuations. Does it make sense? So you can't know when it's going to happen, and basically at the end of the day, once you reach the log of the number of events versus log of the size of the events fall into the same line. Okay? No. Yes. So very big events are going to happen. Okay, no matter what. Very low probability, but they will happen. Very small events, they will happen much more often. And this is basically connecting the system over over all sizes available to the system. So hence the very big events actually depend on very small events. That also prohibits predictability, etc. Yes?
Can we calculate that slope?
You can calculate that slope numerically for a model, but I don't think that there is a theory that will tell you what the slope is going to be.
Is this the same as 1 by f noise?
Yes, yes. Yes, 1 by f noise, because it's also in the title, 1 over f, an explanation of 1 over f noise. So what have you heard about 1 over f noise? Okay. So what do we mean by 1 over f noise is that systems that have time scales of all sizes. Like there are some stars that are flickering. Sometimes they flicker every 2 minutes. Not every 2 minutes. Sometimes between the flickers there are 2 minutes, sometimes 10, sometimes a year. This kind of stuff. As I mentioned, it's very connected to the earthquakes, and that also explains the Richter scale. Why at all we have the Richter scale? Because we noticed that log of the size of the earthquakes versus log of the occurrence of the earthquakes is a line. So we called it a logarithmic scale, right? When we say Richter scale 5 versus Richter scale 6, it's a huge, huge difference, right? Because it's logarithmic. It's like comparing 10 to the 5 with 10 to the 6. But then again, it's 100 times less probable. Oh yeah. Attendance. Any questions, comments, ideas? So, did you follow the arguments which leads to fractal structure, at least in the terrain? Because there are events of all sizes. It's not like Ising model where you have to tune the parameter. It actually self-tunes to that.
By the way, will we be able to get that logarithmic plots in our program as well?
Yes, we will.
Oh, all right.
We will. We will do it next time. We'll do it next time.
And does the slope of that logarithm depend on the size of our grid?
No,
What does it depend on?
just the system. Okay, like, what do I mean by that? For example, how can you change the system? You can say that it starts toppling after it reaches 8, and it topples to not von Neumann neighborhood, but Moore's neighborhood, like all the 8 cells across it. So you change the system itself. Maybe, that's a good homework. That's a good homework. So, because I have an awful homework on this subject, so it's better to do that homework. Okay, so the slope will not depend on the size of the system, because no matter what size, okay, what will change with the size? Let me tell you what will change. Do you see at some point this linearity goes down?
Yeah.
Why is that?
Because there's not enough energy to release that much.
Exactly, because your system has a size. Do you remember the fractal dimension algorithm we had? Like it goes like this and it stops being linear after some point. What was this cutoff? This cutoff was the system size, right? So what we will see in these log-log plots is that it will go linear until it can't go any further, because the system size is that much, can't go further, right? So what will change if you increase the size of the system is that your line will extend further, but the slope will remain the same. Okay? I don't know, but I suspect that the slope will change if you go to Moore's neighborhood. So, because you are changing the system, right? Does it make sense? There is a much easier model that he works on, and some magical number appears on it, and it seems very close to 2/3, but it isn't, and you can't show it analytically, no matter how smart you are. So far, as far as I know, I will talk about that model as well. It's even simpler than this one. This is what we have with this self-organized criticality. The system tunes itself to a particular state, particular dynamical state. It doesn't stay there, just starts flickering in a specific way, and the system loses all information about time and space, has events of all sizes and all times. Okay, we can stop here. We will continue on Thursday.